Thank you.
Good afternoon, everyone, and I'm very glad to be here to present our work with you. The topic is formal verification of discrete event model. This work was cooperation with Zhihao Lu and Yun Guan, and I came from the Capital Normal University of China. In our lab, our research is mainly focused on the formal verification of CPS system. And then now I will give my talk from the following sections. At first is the background. Ptolemy is a modeling and simulation environment used in CSP. This tool was developed by Edward Lee of he and his group has working on this project for more than 10 years. And this tool was very popular in research areas. The main feature of this tool is hierarchical and heterogeneous. For the hierarchical, we can see from the picture here. All the actors can be constructed hierarchically. Another feature is heterogeneously. This means that it can build a model with different model of computation with different MOC. In this modeling environment, it can support many models. For example, a discrete event, synchronized data flow, synchronized reactive, and so on, many kinds of models of computation. These models of computation can build a heterogeneous model hierarchically. So in this picture, the basic component of the model is actor. A means actor. And here we can see directors. The director can express the different models of computation. So in this rectangle, we can see that the director can be any kinds of the directors. This tool give a graphical modeling environment, and we can also do simulations in the environment. But the main disadvantage or a weakness for this tool is it less of formal verification. As we know that simulation can do most of the works to guarantee the correctness and the safety. But for the safety critical systems, formal verification is also a very important way for guarantee the correctness. In this lecture, we present a translation-based verification method for the formal verification of a DE model. Actor is the basic component in Ptolemy. So actor is a tuple. E is the set of actors. P is the set of ports, and the para is the set of parameter. The parameter can specify any kinds of properties. R here is instead of two kinds of relations of port. One is the two inner actors port, and the other is the actor and with the inner actors. This is a more formal semantics for this definition, and all the directors can have the actor, but how these actors are executed, it depends on the director. In this study, we mainly focus on discrete event model. Discrete event model can model timed and discrete interactions between concurrent actors. The interaction between the actors is called an event. All the event has a value and a timestamp. The event is fired according to the timestamp. They are waiting in a queue, and is fired from the hand of the queue. And we can see from this part of the slide, it gives the how to act the um, code for the algorithm for the DE semantics. At the first, the earliest event is fired, and after it is fired, after the execution of the actor will generate the output event. This output event are sorted in the new event queue after all of events are fired, and this director will finish. Um, and here, because of the timing property of the model, so we try to use the timed automata for the formal verification of this kind of model. Timed automata was first was presented by R. But here we use the timed automata model of UPO. UPO is a very popular formal verification tool. And with this tool's help, um, we can generate the model that can be verified more easier. Timed automata is a tuple of 6 elements. L is a finite set of locations, and I0 is the initial location. L initial locations. A is a set of label. V is set of clock variable, and I is a location constraint function. E is a set of edge. Each edge has the guard, the synchronization, and the reset. For the semantics of timed automata, there are two kinds of transitions. One kind of is the elapse of time. For it means that the automata can remain in the location, just waiting the time elapsing by. Um, Another is location switch. The automata will switch from one location to another location. If the guard is satisfied and there is another synchronization synchronized with it. Now let's see an example of timed automata. This timed automata have the location N and the location M, and this is the guard. If the guard is satisfied, only the guard is satisfied, and there is another synchronization with A, this transition can execute. Another kind of is time elapse. Now let's see this one. Is the location is N, and the next location is also next state. The location is also N, but the value of clock variable X and Y have changed because the timing passed by. So this is the small example of timed automata. And our work was to design the mapping rule and a template library, because in the director, there are some small actors that has the fixed function. For this kind of actor, we don't need to translate to complex timed automata. It just gives some small function. For example, the time delay actor just delay the time. for 1 or 3 or such like this. Mm, for this kind of actor, we give the template and form a template library. For each template, we just for the translation, we just need to get the information of the actor and try to fill the parameter according to this actor. And the mapping rule is used especially for FSM actor in DE direction. Now let's see this picture. In this picture, there are 3 actors, and this is an output port, and the P1 is an input port for A2, and the P2 is an output port for A2, and the P3 is an input port for A3. And for these 3 actors, we will translate these every actor to an timed automation. The port of the actors are translated to the synchronization of this timed automata. Now we can see that for this P0 to P1, for this connections of the 2 ports, we translate to a synchronization P0, P1. And this is another synchronization with the blue line. And all the synchronization and the output value are defined as global data, and the input value and the parameter are defined as local data. This is let's see the mapping rules here. This is the syntax element of actor. This is the syntax element of timed automata. The mapping rule tell us how to mapping the syntax of actor to that of timed automata. So there are import, output, and the parameter, and make some functions. The import and the parameters are mapping to the local here, and these are the naming of the timed automata. The outputs are mapped to the global data, and the functions are to the transitions of the template. Template means the timed automata. FSM is a special, more complex part for this transition, because FSM is it's a dynamic. It's not a fixed actor. When we build a model, we can build any kind of FSM model. So this is a rule for the SM actors. The different of FSM's translation with timed automata is that it just have guard and reset. Guard means that it is a precondition for the transition, and the reset means that after this transition, these operations will be executed. But in timed automata, there is another element. It is the synchronization. But the synchronization in DE actor is expressed by the in and out port. So we must match the in and out port with the synchronizations here. For the transition with I input event and I output event, we have to translate this transition to the transition like here. We end 2 locations is S0P and S0D, these two locations. The for S0P is used for helping the S0 because the data in the port can arrive at any time. We don't know when it will arrive, but here we have to this precondition means that we have to check all the ports. So this S0P, this location here was used to check if all the all the variables from the port are received, and with the same meaning of S0D. It means that we have already sent all the output to the next actor. And the next picture shows the transition with I input and no output event. So here we can have we just have one additional locations for the input to receiving the input signals. And this transition is no input event and I output event. So we just have an additional helping locations for sending for the output port. Consistency analysis. Consistency is a very important problem for the model translation. We have to guarantee the consistency of these two models. The order of the actor fires is the same as the order that the automation runs. Another reason is that two models have the same execution paths. We check this from the simulation of these two models. The third reason is that all variable values at each execution step of these two models are equal. And we also implement this tool and plug this tool in the autonomy environment. Here is the input of this tool is the autonomy model, autonomy DE model. We first pass the DE model and we get the structure information of the actor. And we have already has the template library. We just need to analyze the parameter of these actors and get the timed automata model from the template library. If we have the FSM actor, and we will use the conversion of the translation rules to get the TA model. If we want to do the verification, we need the properties. So here we have give one place that we can type the verification formula here. After that, we give two choices for the verification process. One is the generated the UPL file and do the verification work in UPL. Another is to just do the verification in autonomy because we add a button and verification button in the autonomy environment. And this, if we press this button, it will call the verification engine in UPA. And then we will get the result. Here is an example of how to verify the autonomy models. This example is a traffic light control system. This is a road, and the lights have a red, green, and a yellow light for this road. And for the pedestrian, there are two lights. In this control system, the safety properties is two lights can't be green at the same time. We must guarantee this property. This is the DE model. In Ptolemy, in this model, we have we have 5 actors, a clock actor, and this is car light controller, and the delay of 1 time unit. This is delay of 2 time unit, and this is pedestrian light controller. This actor, we can see inside of this actor. It's a FSM, and it's also an FSM. So in this example, we have 3 particular actors and 2 FSM. And when we generate the model from the DE to the timed automata model, we get 5 timed automata. The first one is car light controller. And here we can see that we add some additional locations here. This is the pedestrian light control automation. And here also we add 2 for the input and the output to handle the input and the output port. This time delay are template that we have defined. This is the for one time unit delay. This is defined by the parameter here and here. Another one is clock automation. So for this particular actors, it seems more simpler. And we can do the verification in UPO. This property was written in CTL formulas. AG not can car road green and pedestrian green means that the 2 variables can't be green at the same time. The second property is that there is no deadlock. So we can check that the 2 properties are both satisfied. Let's see the conclusion. In this work, we designed a translation-based verification method for the DE model. And then we developed a plug-in and integrate the tool into the Ptolemy environment. For future works, timed automata, there is another difficulty part of FSM in DE model. It is the model. It means that the state of the FSM can be refined as an FSM. So how to deal with this part is a difficult point. For the existing method, flattening is a way, but flattening may cause the model model explorer. So we may try to use the synchronization of this automata. Another work is to verify more complex systems and to check if this work are the solidity of this work. Another challenging is build how to get a model for different directions. That seems very challenging. That's all. Thank you.
Okay, thank you so much for your nice presentation. So is there any question from the audience? So there is a question from Zhu Shihao. What about the complexity of the converted time automata? Will it be too complex to verify?
It depends on the input model of this example, as we see that for the particular actors, the timed automata are not very are simpler, but for the FSM, we add additional locations for the import and the output. I mean the number of the state in the FSM and the number of the locations in timed automata, just and 2 additional locations for the FSM. But if the input models are very complex, I think the generated model must have the consistency with the complexity of the input model.
Okay, thank you. So another question relates about the time to verify the automata. Can you give us some idea of the time that requires to verify the automata?
You mean the timing properties?
No, I mean also yes. But okay, there is another question. What are the other actors and what are the essential difficulties to implement?
How can I see the question?
Okay, the question is in the chat. So what are the other actors and what are the essential difficulties to implement?
Other actors.
Yeah, I also
we have implemented, and there are many kinds of actors, so many actors. We just choose the most commonly used actors for DE director. As I think, as I remember, we may have realized more than 10 special actors, and give a mapping for the FSM.
So maybe if Q1 can elaborate more about the question.
For the timing properties, as the for the DE model, the most timing is the sequence of the event, and the timed automata can easily modeling this feature. For example, the time delay actor in the Ptolemy model, and we can easier build a model for this actor. So the timing properties are more easier to realize in this model, I think.
Okay, thank you. Okay, if there are no any other questions, I might invite the speakers for the panel, and then we can start the panel discussion. So Luca, is it here? And Professor Brian? Okay. Okay, since maybe we can start and later they can join. So we have a few topics regarding the this panel discussion. The first topic regards the fairness in AI, especially in when we want to test the fairness of AI in software, but also in IoT software and so on. So does anyone want to comment on this? Okay, so no one. Is there any question from that some attendee want to discuss about this topic? Okay, so since the only panelist here is okay, so okay, since no speakers are available, we can finish here this workshop. And thank you a lot for attending this workshop. And see you at ISSTA 2020. Thank you.